Third and final lecture on industry, I'll summarize some case studies from RMI's practice that illustrate both technologies and, more importantly, ways to reframe the design problem. These examples are not about fundamental process redesign like R&D labs do, but about using existing technologies, sometimes from other fields, produce the same products or results with less energy, cost, time, and risk. Both kinds of innovation are important, and they're often more than additive. After capturing the big system boundary opportunities to eliminate muda, muri, and mura, what's left, if not designed out, is a technical production system. Within that narrower boundary, if we leave aside all the downstream savings, and for now we focus solely on producing materials and products that are really needed and are optimally chosen and designed, there are 8 familiar places to look for big savings. Right sizing everything, thermal savings and integration, innovative and distributed power systems, designing friction out of fluid handling systems, super efficient drive systems, water and energy integration, super efficient and heat-driven refrigeration, and advanced controls. Now, most industrial engineers focus largely on item 2. The previous lecture already illustrated the power of digging into the 4th and 5th terms, fluid handling and drive systems, but the other 5 terms have powerful stories of their own. Our efficiency toolkit contains some nifty Swiss Army knives that apply across all categories. So let me first just mention a few of those. A useful first step is to figure out what efficiency is worth and write it on your hand or stick it on your forehead so you won't forget. For example, in a typical clean room, paying 8 cents for a kilowatt hour of electricity, it's worth around $10 present value to save a watt. It's worth $4 per liter per second of exhaust flow to cut the pressure drop by 250 pascals or 1-inch water gauge. It's worth about $150 a kilowatt to make a continuous duty motor 1 percentage point more efficient. If any of you find a chip maker that tells its tool makers, the builders of the chip making equipment that uses most of the fab's energy, how much it's willing to pay them for higher efficiency, please let me know. Same for any other user and its equipment vendors. Vendors who will figure this out on their own and make it into a new value proposition for their customers are still pretty rare. It's as if both ends of the supply chain were each waiting for the other one to innovate. Now, a useful first step that I want to emphasize then is setting up such metrics to know what efficiency is worth. Because if you don't do that, you and your suppliers can't invest wisely in the right amount of efficiency. Now, often the powerful way to save energy in industry is to tell the operators what they're wasting. There was the factory where we saved $30,000 the first year by labeling the light switches. Nobody wanted to flick a switch to see what it controlled because they might turn off something important. So nobody did. There was a hard drive factory that had a kind of a dummy gauge or pressure drop across a giant filter bank. And if it went from the green into the red zone, it was time to change the filter, but there weren't any numbers on it. So I had them paste up a couple of paper scales on the wall. One of them showing cents per drive, the other showing $1 million profit per year, which was a very nonlinear function of cents per drive, because if you could get your price point down to certain levels, you would suddenly jump market share. There are innumerable facilities that have saved amazing amounts of energy and maintenance costs just by measuring stuff. But there are a lot of others that are using poor or uncalibrated or no sensors. And few plants are designed to measure what's needed, and very few present key efficiency metrics in real time to the operator in effective graphics so they can actually make a smarter decision. Now, in this case, Liang Lock saved about half the electricity used by a big new variable speed chiller by resetting its controls so it ran properly with tens of kilowatts less power. We went from the dark blue to the magenta zone. And to persuade the owner to let him do this, Mr. Lee just showed him this graph of measured performance. The yellow line is called the guaranteed performance curve. And if Mr. Lee's retrofit beats that line, if he's under it, he gets paid. Otherwise, he doesn't get paid. And he's paid only for what he proves he's safe, so he measures meticulously. Really good idea. A larger lesson of his practice is that graphs can convey about 3 orders of magnitude more and faster information to the brain than tables of numbers can do. And almost nobody can keep many dimensional state spaces in their heads. So using not a simple 2-color flat graph like this, but 3D graphics with colors, intensities, behaviors like pulsation, dot marker styles, Mr. Lee can and does enable plant operators to visualize the many key variables and the complex and often unexpected behaviors of their technical systems. There's an eminent San Francisco engineer, Zulfikar Kamali, who has a graphic simulator for big buildings. So he'd set down the operator in front of one and says, "Hi, I'm Embarcadero Center, fly me." It's like a flight simulator. And this helps the operators discover that their normal setups were around a local optimum, far from the whole building optimum. So they could gain tens of % overall efficiency just by using the simulator to retrain their mental model. So Zulfi would say to a new operator, okay, so here's the weather report. How are you going to set up the building for today? Okay. You want to save 30% of the energy? You can't do that. How did you do that? And that's when you discover that your mental model is not the way the building actually works. Mr. Lee also equips his real-time building display graphics with alarms. So when any emerging or deterioration, maintenance kind of issue emerges, the system will diagnose it and tell the operator what to go fix before it can waste any more energy. Now, a powerful way to think about how much energy we can save is to ask what is the minimum energy theoretically required, ask how much of that energy we can get for free from natural forces, and then work back to see why the amount we're actually using exceeds that net minimum, often by tenfold or more. As Edwin Land said, you always start with a fantasy. Part of the fantasy technique is to visualize something as perfect. Then with the experiments, you work back from the fantasy to reality, hacking away at the components. Well, often you don't have to hack very hard. So look at this example. It's a 24-story Hyatt hotel in muggy Singapore where Mr. Lee retrofitted a 92% reduction in the electricity used to move air and water. He cut 27 toilet stack exhaust fans to 1. That went from 25 to 1.6 kilowatts. It went from 7 to 4 air handling unit fans, redesigned with low face velocity, as we discussed in the buildings lecture. That went from 45 to 2.6 kilowatts. He used fatter, straighter pipes with no elbows and fewer valves to take the water pumping in the walk-in refrigerators from 22 to about 3 kilowatts. And thus he delivered the same or better services with 7.3 instead of 92 kilowatts, a 92% reduction. The only way to tell he'd been there was the 92% lower electricity use with fatter profits. No magic, just beginner's mind, careful measurement, good whole system engineering, careful observation, or at least as whole system as he could do without being allowed to fix the building itself. That could have raised the savings a lot closer to 100%. In more than $60 billion worth of diverse industrial redesigns for leading global firms, RMI's team has typically found energy savings several-fold larger and often several-fold cheaper than normal consultants deliver. Our challenge was often to understate the likely outcome by enough that the client might believe and engage us. RMI's latest 60-odd billion worth of industrial redesigns typically found about 30 to 60% energy savings on retrofit across diverse industries, paying back in a few years and far outperforming the orange zone in the upper left, where most energy service companies deliver disintegrated design. This is analogous to the Empire State Building, where a noted energy service company offered the same 3-year payback we got, but its disintegrated design would have delivered only a sixth of the 38, later 43% savings we got. And then in new industrial projects, RMI's practice generally found 40 to 90-odd% energy savings with lower than normal capital cost, again, across a wide range of applications. So let me give you a few diverse examples just to illustrate how we achieve results like this. Let me start with a sector in which I've been active for nearly a half century on energy efficiency, and in which RMI's Sunshine for Mines initiative helps major companies switch to renewable energy. So our first case comes from the world's largest platinum mine. It's over a kilometer beneath South Africa, Rustenburg. In 2004, energy intensity was rising. That was squeezing profits. And the chairman, who had been RMI's client in his prior job chairing an oil major, asked if we could help. So feeling a charrette coming on, I hypothesized that integrative design could probably cut operating costs dramatically, save capital cost too, and permit deeper and safer mining, both a huge competitive boost. So the whole top management team, including the chairman from London, participated in the entire charrette, which sent a strong signal of interest. It drove faster cultural change and deeper commitment. Removed a lot of fear about what the boss might think, because the boss was there to say. And our joint team found a 43% energy saving potential, whose orderly execution would take about 5 to 7 years. The average payback was much shorter than the execution schedule. It was less than a year for 43% of the 108 projects. We also found major benefits for the workers' health, safety, and productivity, and for recovery of the PGMs, the platinum group metals that the mine produces. In absolute terms, the savings were very large. They were well distributed across the activities in that sprawling site. So there was something for everyone, and we could glimpse even more opportunities to be explored later. Now, here's a simplified chart of the successive energy savings we found in a wide range of functions, showing the biggest first at the left and going to smaller ones rather than showing the cheapest first. And they're color-coded by where they were in the operation. The two biggest chunks were reducing concentrator waste and improving or eliminating compressed air. That's the costliest energy carrier, the one that's seldom actually needed, so we try to design it out everywhere we find it. Now, the broader context was a long-term industry-wide shift to greater sophistication and often to biological metal recovery. We suggested early trials starting with existing tailing piles of certain plants that hyperaccumulate metals very impressively, even gold, of which carrots and Indian mustard and certain algae are very fond. The industry is now active in such research, but meanwhile, we had a very big old mine to deal with immediately. Now, mines use a lot of diesel fuel, moving heavy stuff around in immense trucks with tires up to 4 meters in diameter. Each tire costs over $40,000. This truck hauls 450 tons. And in the South African surface mines haulage, we found that careful attention to 27 kinds of improvement, later we found more, could save about 28% of the diesel use for ore hauling, leveraging further upstream improvements. How do you do that? Well, you start downstream. You systematically reduce demand for moving mass. 2/3 of the mass you're moving is the truck, not the payload. You minimize power demanded to haul each ton. You minimize the energy supply to deliver each unit of power demanded, and you optimize the energy source. So that's left to right on the upper big arrow. Now, the eye chart under that is how we classified and then explored scores of opportunities in 11 steps of surface haulage, breaking it down to be more and more granular. Now, you probably can't read such small type. I just want to illustrate the richness of the menu of choices and opportunities you find when you really drill down. And you might want to come back and study this chart further just to see how granular it gets. All trucking problems merit this granular approach, and then you can electrify the mining trucks, like the 400-ton Komatsu at the lower right. That even gains net energy if the loaded haul is downhill, that is, the mine is above where you need to get the ore to. Or trucking itself could be designed out using newer innovations like Barrick's rail conveyor, is a cross between a conveyor and railway. Now, the highest modern mining ambition is to send only robots underground, not people. But this South African mine had many thousands of workers deep underground with important energy and ergonomic issues. The working conditions we observed were all legal, but they conspicuously failed to give the miners the conditions they needed for productive, healthful, and optimally safe and happy operation. So we began with first principles of thermal comfort and with these kinds of ideas. So first, what drives the relationship between comfort and productivity, and notice it includes metabolic efficiency and state of mind. We wanted to deal separately with temperature and humidity, and separately with cooling, ventilation, and filtration to see if we were really combining them the right way. We didn't want to be burning stuff, especially high sulfur diesel fuel, as they were underground. And we didn't want to create waste and toxics. We wanted to clean the air and ventilate for enough oxygen and getting rid of CO2 and filtering out dust and stuff first, and to systematically minimize humidity, because it's hot down there and it's better to be in a dry sauna than a wet sauna. Then we could reduce the humidity with a desiccant, which soon could be biomimetically passive. There are insects that know how to do that. Or we could have a condensing way to get moisture out of the air, and we can reject humidity into exhaust air or water. You notice on the right, one of the things we did was paint the black rock white so it would bounce the light around better and you could see what was going on. Now, we didn't yet know how effective radiant cooling could be, but now that could offer an even better option. Now, to moderate the sauna-like conditions so far underground, after minimizing unnecessary humidity, we would, all of which was introduced, but not very thoughtfully, we would minimize the heat gain from the rock that's hot underground and from the mining equipment. And we would focus on cooling people rather than cooling rock. The rock has no comfort sensation. We would do the usual passive first technology sequence. We would deliver ventilation very precisely. And since each square meter of cross-sectional area in the deep vertical shaft that goes down into this underground mine, a kilometer or more, is extremely expensive, the existing mine was trying to blow cool air at fairly high velocity from gigantic coal-fired electric chillers and fans at the surface down the kilometer deep shaft, and then it was supposed to bounce along the horizontal workings with giant fans. So barely a hint of cool air ended up reaching the miners several kilometers away. So instead, we suggested moving unwanted heat up the small shaft in thin heat pipes, enormously more heat capacity than air, and then rejecting heat to very efficient cooling towers or passively radiating away to the minus 40-degree desert sky. Now, we noticed some worrisome issues around health and safety, especially since a third of the workers were HIV positive. I think it's a lot fewer than that now, but still a plague in South Africa. The working environment was very stressful, and the workers got rehydrated only on break halfway through their shift. And by then they were too dehydrated to catch up. And that compromised their attention, safety, and underlying health. So we brought along some Camelback hydration gear for show and tell and demonstrated continuous, just suck on the tube hydration and adding electrolytes to the water rather than just offering sugary and diuretic tea. The working areas lit the black rock walls very poorly with strings of hot, glary, incandescent lamps. So we first had the rock sprayed with white paint and then with efficient indirect light. Like the miners, when we were down there, we each wore a heavy lead acid battery belt pack connected by a thumb-thick cable to a Victorian incandescent helmet lamp. But our show and tell kit included featherweight cable-free LED mountaineering and caving lamps that even back then in 2004 gave tens of times more light per kilogram, more reliably, more durably, with better control, and with enough electricity left over to run an efficient little fan to cool your scalp through a helmet slot. Well, today the white LEDs have become about 3 times more efficient still, further improving ergonomics and safety. Our show and tell also included Spelunkers phase change vests that can keep a miner's skin at 15 degrees C for more than a half shift. And then at break time, you can recharge it by dunking it for 20 minutes in an ice water bath, chilled by an absorption chiller run by waste heat from the machines. And then add all that to better hydration and physiology and a nicer workspace, and the miners could become far safer, healthier, happier, more productive, less fearful. These benefits are all probably more important to the mine's bottom line, let alone society's, than all the energy savings we found. And it illustrated how the old mentality of just complying with regulations can distract managers from the right and the best business choices. Now, the smarter comfort provision would shrink or eliminate the giant chillers and their coal-fired power supplies. Cutting the steam losses would avoid new boilers. We found ways to improve the mining operation itself, especially by helping miners to assay the rock real time to see what was worth hoisting up the shaft and processing. For example, using a backpack-sized mass spectrometer built by an old friend in Tbilisi for Soviet asteroid sniffing satellites. And we suspected there was also major scope for rethinking the concentrators and their controls, although we didn't actually get to do that. But all of these things work together. Now, having seen how much mechanical systems can improve in buildings, you won't be surprised that, especially with Mr. Lee there, we could save 85% of the underground cooling and air handling energy, starting with 41% savings for measurement and maintenance on the equipment, and then 40% load reductions at the mining face, leaving little to save by the last step, which was a redesign saving 57% of the chiller system's energy. So we started at the end and worked back. And then, as always, there was a lot of little stuff that really added up. Item 2 really got their attention. When we graphed the experience of a platinum atom moving through the process, we found it was heated to 1200 Celsius by coal-fired electricity, and then quenched with water, dried with more electrically heated air, and then it would repeat that whole process as many as 3 times, because the otherwise very capable engineers had not focused enough on keeping hot things hot and dry things dry. They were kind of embarrassed to notice this and change that process in a hurry. They were just too close to the problem to have seen what they were doing and that it needed fixing. Now, the next to last item was also interesting. Miners were being paid by the ton for whatever they sent up the shaft. So some sent up not just platinum ore, but also everything from dross to scrap lumber to, who knows, dead donkeys. Tons is tons. So be careful what you reward. Remember the same story earlier from the cider maker. You got to get the right metric. We even asked whether every customer needed the mixture of platinum group metals to be tediously separated into individual metals with very similar chemistry. It's all inner shell variation, all purified to London Metal Exchange specs. It turned out some customers could happily use the raw mixture as is and skip the whole costly refining step. So adding up all the opportunities that the company's experts and we identified together, we ended up both with a severely practical agenda and with a bracing vision of what similar thinking could bring to a future mine. I'm sorry I can't tell you what happened. They certainly didn't get this far. And unfortunately, the operation was later sold. And all the people I worked with have retired or left or died. That's not unusual. You know, it's often hard to sustain continuity in long-term industrial relationships so you can track what happens over decades. But the lessons can live on, if not in that client's culture, then in others inspired by the example, as long as the stories survive. And wherever our original partners ended up in the industry, they took those learnings with them and probably shared them. Now let me end these mining examples by illustrating 3 levels of ambition: less energy, no external energy, and no mine. So the first level is a summary of what we just saw: how to save 43% of the energy by retrofitting a big platinum mine. Okay, so far so good. And you know all that. Now, a second level of ambition would be to go net zero in a proposed West African iron mine. First, we would find enough megawatts to eliminate the normal need for grid power or an on-site power plant. First, we would start off running the whole mine on the gravitational energy of lowering the heavy ore down to the port in baskets on a ski lift run backwards as a 92-93% efficient electric generator. And that plus hydropower from selling a valuable perched water table, which was a nuisance up at the mine, but needed at the dry port below. So just running the water downhill in a pipe with a turbine would give us more power. And each of those renewable power sources would replace other investments to deliver the ore and drain the water, but they would avoid normal power supplies, reduce capital costs, eliminate energy operating costs, increase security, a lot of advantages. I don't think that one's been built yet, but it remains a good idea. And you know, the people that make the ski lifts in Austria are happy to sell you the same product backwards. It's already in their product list. Now, third, after finding many conventional improvements at a nearly new high Arctic industrial diamond mine, I got curious about what's called the grade tonnage curve, relating how many diamonds there are at a ton with how many tons of diamonds there are. So I asked him, how do you assay the billions of dollars worth of diamonds in your carrot-shaped kimberlite pipe? Well, they explained how they dissolved the kimberlite in hot caustic soda, sodium hydroxide, leaving only diamonds, which they then weigh. That gave me an idea. So over our parting dinner with the executives, once they become a bit uninhibited, I suggested that they build a sandworm, like in the Frank Herbert's Dune novel, whose gut contained hot caustic, and let it munch its way down through the kimberlite, pooping out diamonds. Recovery would improve because any goose egg sized diamonds wouldn't be broken by blasting or milling before they were detected. Moreover, the entire mine and bill would no longer be needed. Now, even if the sandworm's gut had to be made of pure unobtainium to withstand the corrosive hot caustic, nasty stuff, the total cost should still decline dramatically. So the mine manager was exceptionally open and imaginative. And to my delight, he said, you know, even though we're already a third of the way through the mining plan, I'm prepared to test this notion, and if it works, switch to it immediately, even if it means abandoning all that existing equipment. Wow, I love that reaction. Unfortunately, he got hired away before he could do that. Now, a fourth level of ambition would be to start all the way downstream by not needing the mineral in the first place. There are a lot of ways to achieve that and compete against mined minerals, as we saw in my 2022 essay on solutions to battery mineral problems. And in general, the wider your system boundary, the bigger the savings and the lower your costs. Now, so far, I've mentioned only technological solutions, but new business models can be even more powerful. You see, mining companies are not just capital intensive, long lead time, price takers in a volatile market, just a recipe for headaches. They also sell tons in a world that will use fewer tons more productively. So how about leasing a metals services rather than selling tons of metal? Let me ask you, where is the world's richest copper deposit? Papua New Guinea, Chile, Zambia? No, it's actually under Manhattan in the vast networks of power and signal wires. Unfortunately, that copper was not installed very retrievably. But if the firms selling tons of copper to the cable makers had instead leased a conductance service, it would have had an incentive to develop optical fiber, wireless, negawatt, and distributed generation alternatives to free up copper so it can get back and lease it to someone else. That would have been a much better business with steady long-term revenues at a constant price. So beware of business models that misalign your incentives with your customers' incentives. Mining companies now make the same error as energy companies that sell electrons or molecules, ensuring that when customers improve their efficiency, that will cut not the supplier's costs, but the supplier's revenues. But lately, one of our mining clients was developing ways to profit from its mastery of gold logistics, helping existing gold inventories go either physically or virtually to where they're most valuable without having to mine any more gold. Sooner or later, someone is going to do such virtual mining for the services that we now provide by copper and by many other metals. They will lease services rather than selling tons. Maybe you'll be a part of that. Now, our next heavy industrial example is a giant cryogenic plant in far northwest Australia, turning natural gas into minus 161 Celsius liquefied natural gas, LNG, for marine shipment. When we arrived at the site in a blazing desert to lead a charrette, the outdoor air temperature was about plus 54 Celsius, with kangaroo-sized giant lizards running around. We found ways to save upwards of 40% of that plant's energy on retrofit with a few years payback, or in an expansion or new build, how to save upwards of 60% at lower capital cost. Saving energy is it's a bit like eating an Atlantic lobster. There are these big obvious chunks of meat in the tail and the front claws, but there's a roughly equal quantity of tasty little morsels hidden in crevices that require skill and persistence to recover. We need to go for the whole lobster. Or to pick a different culinary metaphor, Mr. Lee, who was on our charrette team, says, like Chinese cooking, use everything, eat the feet. So let's go look for some juicy feet too. Gas is becoming globally fungible even in markets not fed by pipelines, thanks to LNG made by giant chillers, really important in dealing with Putin's war. RMI helped to redesign several of those multi-billion-dollar plants. And this diagram from our first project does not show the throughput of natural gas molecules that get liquefied. Rather, it shows the fuel gas burned to process that product, to do the liquefaction. And it turned out 73% of the fuel gas, which otherwise could have been liquefied and sold, instead got turned into 0.8 gigawatts, billion watts of waste heat. nearly all very hot, 420 to 540 C. And then throwing that heat away required considerable energy and investment. So to repeat, in this supposedly optimized process run by one of the world's top oil majors, only 19% of the fuel gas ended up making the main LNG product. Now, the big tail of this juicy lobster was its power plant, which used simple cycle gas turbines run inefficiently and hence expensively. If we could save a little electricity, we could shut down some turbines altogether. And to facilitate that, we could start adjusting operations for better load management, like making liquid nitrogen at night when it's cooler and the turbines run better and the plant's drawing less power. We were also struck by the way the plant was running multiple turbines very inefficiently at part load in case one of them failed. And we had found the same practice on the US Navy's Aegis cruiser, USS Princeton, where our suggested fix was what we called virtual trail shafting. That means you spin an unfueled turbine synchronously with a fueled one that's at full load, not by physical trail shafting, that is both turbines on the same shaft, but by coupling them via an electric motor generator pair. And then if the fueled unit fails, you just spray fuel into the other one that's already spun up, you light it off, it's already at synchronous speed, you don't have to spool up, so you never lose power. There's a little handoff glitch, very brief, very easily handled by power electronics. Now, rather than blowing costly compressed air to take dust off filters, we would send a sharp pulse into a woofer loudspeaker to blow it off. We would probably want to boost the turbines with a little inlet water spray. Remember, it's extremely hot and dry there, so that it's the air cooler. Gas turbines are often designed to work in jet airplanes where it's really cool up in the upper atmosphere. Better still, we could go combined cycle, or of course, renewable, which was not cost effective back then, but it would sure win today. The lobster's front claws came from the 3/4 of a gigawatt of heat that the operators were paying heavily to throw away at 400 or 500 plus degrees Celsius. Wow. Well, a lot of heat, very hot. Some of it could directly replace furnaces and electric process heat that were simultaneously operating on their own fuel. But we could do a lot more with it too, cascading through heat reuse to cool production, desalination, even a Rankine bottoming cycle to make more electricity. And then brine from the desalination could also be sold to the nearby salt works. You might wonder, how do you throw away that much heat, 3/4 of a gigawatt at high temperature? Well, with 700 fin fans that used 15 megawatts of electricity just to spin their fans, that was $21 million worth of electricity, present value. And the fin fans could be run much better, but we had other ideas. After minimizing the heat to be rejected, we would scrap the existing fin fans, which are 2/3 of a century old designs. We put in redesigned ones, micron misted on the inlet, get it a little cooler with very efficient motors and adjustable speed drives, and above all, with aerodynamics much better than the standard 1940s design antiques we saw, which are standard in the industry. So the new design would apply basic physics like this. And Mr. Lee figured these would cost little more. They'd save about 80% of the energy to run the fin fans. They'd work better for longer, and they would pay back very quickly. And now this design is being refined to support potential manufacturing. Now, this efficiency lobster also has lots of tasty little morsels you have to dig out of the body crevices and legs and so on. So some of those may by now be obvious to you, like capturing pressure letdowns and expansions, or painting cold stuff white when it's going to sit in the sun, or shifting heat between the parallel chiller trains to help keep the whole plan tuned up as the winds shift. But the funniest discovery, the last item listed here, is the $1 billion we found simply lying on the ground. Huh? Well, on arrival, as we walked the site, I puzzled our host by keeping my weapon of choice, which is an infrared thermometer, pointed mainly at the ground. Why? Because the ground, I noticed, was paved with black asphalt and dark gray concrete. Mounted above it were several hectares of plumbing that they were trying to cool to minus 165 Celsius. So based on California cool roof results, I figured that covering the ground with anything white and cheap, white sand, crushed limestone, oyster shells, whatever, could cool the site by about 10 or 20 Kelvin. Well, that evening we ran regressions on the efficiency of the plant as a function of ambient temperature. And next morning we announced that whitening the ground would be worth about $1 billion present value. By the way, the pipes themselves, the cryogenic plumbing, those were all beautifully sheathed in shiny stainless steel. So I pointed the infrared thermometer at one of those too. A little thought experiment. If you take 3 pieces of sheet stainless steel, one bare metal, one painted black, one painted white, and you stick them all in the sun, which will get hottest? Probably the bare one, because stainless steel has very poor infrared emissivity. Even black paint probably runs cooler, but white paint costs the same. It's just physics. Now, there was also a nice lesson about starting all the way downstream. The next to last thing the LNG sees before it goes aboard the marine tanker is a big spherical tank where it sits for a few days. The LNG in that tank has to be continuously circulated because if it stratifies, it can suddenly roll over and break the tank and possibly incinerate the whole multi-billion-dollar facility and people for miles around. Well, we found that the LNG was being circulated by an immersed motor and pump system with a combined efficiency of 68%. Okay, that means 32% of the power you feed into it is boiling off your LNG product, heating it up. But it would be worth paying a lot for a high temperature superconducting motor like the Navy uses that would run a good pump at a combined efficiency of 89%, reducing the heat released, hence the product wasted by boil off by about 2/3, and leveraging all the savings back upstream to liquefy that gas that's getting wasted. Well, beyond that, remember Jay Harmon's biomimetic rotor whose ring vortex flow can circulate 4 megaliters of water with 24 watts? Well, that or an aerator solution that replaced 137 kilowatts with 0.56 kilowatts could get us to about 99% motor and pump efficiency with over 30 times less boil off of precious product. By the way, even those giant tanks have been painted dark green because somebody thought that would make them look pretty. We suggested white. So what's the very last thing the LNG sees before it goes on the ship? The pipe from the tank to the ship, including the loading arm. Surprise. In between cargoes, those components are not kept cold. So quite a lot of precious LNG never gets into the ship. It's vaporized first, trying to chill the pipe that's long been baking in the tropical sun. It's pretty obvious what to do about that, isn't it? Well, nobody had bothered because it wasn't part of the plant. It was just some miscellaneous dock stuff that those guys worry about. So think of the leverage from avoided LNG loss at the dock all the way back upstream through the whole plant. And you start to see why that's really valuable to fix. Now, there were some other cool questions that we didn't have time to resolve. Maybe the plant was more reliable than was economically optimal. Paul McCready taught me that when he had just won the Trans-Australia Sunrace solar car race, but he was griping that he hadn't had enough flat tires. Huh? Well, what he meant was his tires were using a bicycle-style flip lever for quick changes, but if he'd used a thinner tire tread with less rolling resistance, he would have saved more time, gone faster in the race than the extra time to change tires more often. So he would have made even better time and won the race by more if he'd had more flat tires. That's really keeping your eye on what you're trying to achieve. You're trying to win the race, not to minimize flats. Now, other operational changes could also make sense and make money. And perhaps the CO2 removal process could be improved. The biggest untested idea from Mr. Lee was instead of using one propane chiller with a huge lift, raise its efficiency by half by starting with cooling towers, then going to minus 40 degrees with ammonia chillers, and then going down the rest of the way to minus 165 C with propane, or maybe propane plus one other method, but starting with a chiller lift that's at least 90 degrees C smaller. It's more capex, more complexity, three things instead of one, but we would get the water and heat for the first two steps for free from all that waste heat that we're now paying to throw away. So it's worth thinking about. So you can imagine a kind of, well, to mix culinary metaphors, 5-layered wedding cake. Efficiency everywhere, combined cycle power generators that run the chillers directly off the turbine shaft, supplemented by variable speed motors. Using waste heat from the turbines, ammonia absorption chillers to chill the process streams, and maybe the turbine inlet air, since aeroturbines are optimized for airplane cruise altitudes, not for sea level in a blazing desert. Evaporatively cool the gas turbine inlets too, eliminating their helper motors. Then off the bottom of the ammonia chillers, distill water for use in sail, along with salt and brine byproducts. Use the sweet water in very efficient cooling towers and to micromist the inlet air to the efficient fin fans and maybe cascade some cooling tower exhaust air to fin fans. And probably more integrations after that. So a key insight is that when you're thinking about integrating heat flows, think also about how to integrate and create new value from water flows, especially if you're in a desert. One sad footnote, our client loved our findings, but couldn't implement most of them because a partner firm in the consortium refused. Our client even offered to pay the entire retrofit cost, but take only its share of the savings. That offer was likewise rejected. I guess there's no cure for stupid. For our next case, Eric Wadless, then an RMI practitioner, kindly shared some slides from an oil refinery design project. This new build refinery got derailed first by a market crash, then by the pandemic, so we don't know if it'll ever get built, but it holds some important design lessons. Of course, refineries make us think about controls. Conventional refineries may boil and recondense product molecules 15 or 20 times because most operators monitor product quality only periodically, flying blind in between, and then they have to redistill to unnecessarily high purity to be sure they'll always meet spec. This is called over-refluxing. It uses 30 to 50% more energy than a continuously monitored process. Now, this refinery's all-digital design would also fix another big problem. Most process plants control flows and reaction conditions based on measurements of what already happened, not on anticipating what's about to happen. That wastes materials and capacity, it degrades quality control, it needs extra processing to restore degraded product quality. So in the new refinery, we could use look-ahead controls that anticipate the conditions in the process flow before it arrives and achieve exactly the temperatures and pressures needed by the time it gets there, rather than overheating or overpumping as normal. So adding sensors and control algorithms can thus ensure that the process will make it right, make it once, and then stop. I've heard that the world's most efficient refinery in India now does this. I want to go see that. Now, our new refinery could thereby probably achieve zero over-refluxing, zero slops, zero flare. These are all important forms of muda to be designed out. You could also use mass-produced miniature or distributed distillers and hydrogen reformers that may be cheaper and surprisingly may be more efficient than centralized ones by eliminating column reboil. Now, as you would expect, Eric's team also worked on the proposed refineries, pipes, pumps, and motors. A conventional crude distillation unit at the front end of a refinery looks roughly like this. It costs over $30 million to build, and about 36% of that investment is for piping. So Eric rethought it. You'll see at the bottom a heuristic change similar to ours that he used in presenting this work to the client. Now, he asked where the pumping energy goes, and he found fat opportunities to wring a lot of it out. Notice that only a small fraction of the pumping power was overcoming pipe friction, which could in turn be greatly shrunk. So we looked at the theoretical minimum. And a standard nominal design would use about 12 times the theoretical minimum pumping energy, enough to run about 3,600 average US homes. But redlining the standard design highlights opportunities to untangle the pipe noodles. You see something they missed? Look at the lower right diagram's lower left end. Where's the Y joint? And underneath at the far right, maybe that connector could just run in a big arc and eliminate two elbows. Now, always elbows to get rid of. Now, the result of that first pass at untangling the pipe spaghetti was much simpler and several folds smaller. Look at the enormous shrinkage in the footprint. Wow. And a practical design would use about twice as much pumping power as the theoretical minimum, but roughly 6 times less than the normal design. That's pretty good for starters. But then you had to satisfy insurance and health, safety, and environment, so-called HSE requirements. That spread things out again a bit. And although you can still see some further opportunities for replacing pipe elbows with arcs and diagonals to cut friction and shrink pumps, I think if you look around there, you'll see a few more things. In this case, tripling the pumping energy for required physical separations between pieces of equipment. Now, often there are other ways to achieve those HSE goals by other means, but let's leave that aside for the moment. I'll just mention that on a recent cruise ship project, intimately involving the safety authorities, who are called the Classification Society, in the design process from the start, avoided many expected issues, and often it would reveal smarter, cheaper solutions, many of them suggested by the safety authorities. So I would suggest industrial plant designers always try to engage their HSE regulators up front in collaborative design wherever you can. They will often have smart ideas. They'll be fully informed and primed for prompt approval and internal consensus building if they were at the design table and therefore understood the design logic. At any rate, repackaging the result did not completely fix some layout issues you can readily spot, like around the lower left corner. But wow, is that simple compared to where we started? Much simpler and smaller than the original standard design. I'll just go back to this one again. That's the improved version. That's the original version. And after adding a little more pumping energy for certain operational considerations, the redesign still shrank the saved pumping energy to roughly $250,000 per year. But most interestingly, the capital cost of the piping shrank by 2/3. You may recall that piping was 36% of the entire capital cost of the unit. So this preliminary exercise made the unit about 1/4 cheaper to build, which is really news in that industry. Now, with more effort, we could do better, but this was a promising start. And we're not even counting the value of the saved space, which for another client's floating hydrocarbon facility turned out to be extremely valuable. And that revealed some novel compactness opportunities that are now also being exploited on land. Of course, this whole example begs the question of whether to build a new refinery at all. Super efficient and electric autos, trucks, and planes will not need refined oil products. And in that emerging world, the whole concept of a refinery may be obsolete, because in general, the hydrogen in a hydrocarbon like oil or gas can be so much more efficiently used than the carbon that the hydrogen is worth much more without the carbon than with the carbon, even if nobody's paying you to keep carbon out of the air. So an oil owner could often make more profit by removing hydrogen in a reformer than by adding hydrogen in a refinery. Mega refineries save the most energy and CO2 and money, and efficiency can save hydrogen too, not only refined hydrocarbons. So we're always starting at the end. And I think if somebody came to us now and asked us to help them design a refinery, maybe we'd consider shorting their stock. Well, what if we need process cooling, not for making LNG, very cold stuff, but just for the extremely finicky, almost miraculous processes that make microchips? Well, the standard way to do this is big water-cooled centrifugal chillers, but there are a lot of other interesting methods. Let's rank those by COP, coefficient of performance, that is the units of cooling per unit of electricity. Please forgive me a few barbaric units here. In a Northeast US location where we were helping design a new chip fab, we could get over hundreds of units of cooling for each unit of electricity by using a seasonal storage ice pond, actually a slush pond, or probably from the abundant aquifer, or even from Mr. Lee's super efficient cooling towers and pumps. That's 3 super efficient methods. Lake water cooling was about half that efficient. We could get a COP around 20 or 30 with various conventional devices, or up to 8 to 9.5 with electric chillers. Interestingly, the most efficient options toward the top with COPs upwards of 100 would also cost the least to build, but are the least often considered. Now, the psychrometric chart revealed we could get about 70% free cooling from airside economizers or good cooling towers with close approaches. That is the usual design from Mr. Lee with fat, squat, short towers with oversized fill and big slow fans. Now, you can skip the details of the seasonal design estimates, but their bottom line was we could get roughly 10 times better performance from a slush pond and cooling towers than we could from electric chillers. This, of course, startled and dismayed the client's chiller-centric engineers. They rejected the idea as unreliable because it wasn't the electric chillers that they knew all about and were really good at. So I gently asked them, in their engineering judgment, what did they consider unreliable? Was it the freezing, the thawing, the pumping? After an hour or two systematically working through each issue, they became quite comfortable that this weird idea should actually be more reliable than their accustomed electric chillers. Now, we therefore suggested a new local landmark called Mount Sorbet. You dig a hole, you insulate it a bit if you really want to, but that's not necessary. You line it with a membrane or with natural Siberian biopolymer called clay, Gley, that you can make anywhere. Then you use roughly COP 500 snowmaking machines, buy a third-hand one, to spray slush into it on a few sub-freezing nights each year. You cover it with straw or foam or bubble pack, and then you take the 0 Celsius meltwater off the bottom, use it to do your process cooling, drizzle the return water back on top, and make it big enough on 170 acres of idle land in the backyard to last all summer using simple low friction pipes and photovoltaic pumps. So based on simple cost estimates validated from a Swedish project, we found it should cost less upfront, including the front end cooling towers for pre-cooling, than an equivalent chiller plant. So the seasonal ice pond approach was invented by my late friend, the nuclear weapons designer, Dr. Ted Taylor. It worked nicely a few decades ago on an office building in New Jersey and at a cheese factory in New York State near the proposed chip fab. And by the way, if the plant were in a different climate, too hot for an ice pond, if it didn't have even a few nights a year that were a few Celsius degrees below freezing, that would probably make it good for other COP 100 or so solutions that were based on heat. But at the level of conceptual design, this looked pretty promising. We then helped another chip maker discover how to save roughly 2/3 of a new chip fab's energy use and half its capital cost. We could replace, we found all 22,000 tons of chillers, except a few little ones built into certain tools, with any of 3 cheaper to build natural cooling methods that were over 10 times more efficient than electric chillers. The entire design was estimated to save 2/3 of the energy and about half the total capital cost. And the group set 3 levels of increasingly ruthless ambition, which they called no brainer, no regrets, and no prisoners. The owner could also help his toolmakers save more than the roughly 70% shown in lavender for better tool design, chiefly by really mundane means like best-in-class vacuum pumps and power supplies, simply by telling the toolmakers what the savings were worth. And then we could probably do much better because tool loads cause most of the other loads. But this graph does not reduce those other loads correspondingly. If it did, the total savings in the right-hand bar would rise at least 4-fold from a base case that the client initially thought was already close to optimal, and clearly it wasn't. Well, now let's leave the big iron end of industry and look at some pleasingly antique but instructive little IT examples that are about not how efficiently microchips are made, but how efficiently they're run. Around 1992, I had a very small hand in helping IBM design the world's first efficient desktop computer, the Pizza Box PS2E, which was the first Energy Star compliant computer. It had a PCI slot architecture. It had an early LED flat screen, not the old television style with depth. It had a small enough package to lock in your desk drawer. And my little design contribution was to help persuade IBM to make the power supply just as small as a cigarette pack, but very efficient and with high power quality. Came from Sweden. It would cost more, by somewhat under $1, which seemed a fatal objection until I pointed out it would save even more capital costs by eliminating the cooling fan. That would also make the computer silent. That was marketable. And as a bonus, there wouldn't be an air path to coat the chips with dust and ultimately overheat the chips. So reliability would rise, saving warranty costs. And once the different specialists began talking to each other, they thought this was really a good idea. Now, the cultural challenge of whole system thinking in big siloed organizations then became clearer when IBM kindly sent me an early unit on which I then co-authored the book Factor 4. I think we just gave this to a computer museum. But the compact computer was packed in a crate of over a cubic meter, and it had an off-the-shelf external power adapter that probably wasted more electricity than the computer used. Whoever chose that power adapter simply didn't understand its purpose. Now, in 2003, when data centers were springing up that used over twice as much energy to support the servers as to operate them, RMI convened a charrette in San Jose with over 90 industry experts. Together, we found ways to save about 89% of the usual energy use, probably with lower capital cost, faster construction, better throughput, and better uptime. Savings occurred at many levels: system architecture, software, compiling, devices, utilities, integrative design, decompounded loads. Very efficient multi-purpose auxiliaries and power and cooling systems saved huge amounts of capital as well as space and energy. Indeed, it would have been feasible to make the data center a net power reducer. We also paid attention to business aspects. For example, we found that the root of the inefficiency in normal data center design was an immature real estate model that charged the client, the tenant, by the square foot, even though cost depended mainly on watts. So that wrong metric rewarded operators for cramming more watts into fewer square feet, creating costly and ultimately intractable cooling problems. Well, these findings proved pretty influential. We thought that the data center's input energy could be cut from 1.5 to 2.5 plus times the server energy to 1.2, probably 1.13 times. Later, it fell to 1.08, 1.05. This ratio is called PUE. It's now commonly not over 1.1 in the biggest and best data centers. The best PUEs in the world include NREL's 1.04. In other words, the whole data center uses only 4% more energy than the servers use directly. They did that with variable speed fans, blade servers, efficient power supplies, low energy cooling methods, and 70% virtualization. Bitfury in Tbilisi, Republic of Georgia, has a 1.02 using two-phase immersion cooling. But the Uptime Institute reports that in 2020, the global average data center's PUE was still 1.58. That's better than the 2007 average of 2.5, but it's still bad. In contrast, Google commendably posts its progress each quarter. It's got to an average of 1.10 if you include all site overheads, or 1.06 with a narrower definition, and its best facility, counting everything, is 1.06, really good. Of course, remember where we started 2 decades ago, getting on for, well, more than that. The hotter chips were actually pretty good for cooking snacks. That's a real egg. A Wintel rack-mounted server 2 decades ago cost around $2,000. It looked like this, complete with a 160-watt power supply and 9 fans. Well, now when you can put 2 terabytes of fast, non-volatile memory onto a little tiny thumb drive this size, I dare say you could far outperform this entire server with 1 chip at less than 1/3 the cost. Well, first though, the late Chris Hipp used the late chip firm Transmeta's high miles per gallon 6-watt Crusoe laptop chip to make a stripped down and quite capable early blade server that used under 16 watts. You could fit 72 of those blades in what's called 9U of height. That's 40 centimeters of rack height. And 20 years ago, cost just under $1,000 per blade. In 2001, Dr. Feng Wucheng at Los Alamos built what was called the Green Destiny supercomputer, shown there with the late Chris Hipp. With 240 of those RLX blade servers, it used just 3.2 kilowatts, a couple of hair dryers worth, in a half square meter footprint like a phone booth. And it used 5 to 8 times less power than the Wintel equivalent at 8 times the power density. And yet this was so passively cooled that for the first 2.5 years I tracked it, it had 100% uptime in an uncooled, dusty 30°C hallway at 2,250 meters elevation. Now at high early blade prices, it did cost 50 to 75% more than the Wintel solution. Later it would cost less, but its total of power, cooling, space, downtime, and system administration, those total cost was 90% less. And tested in an iterative science application, it had 7 to 8-fold better energy efficiency than the Wintel equivalent, but with a 3 or 4 times lower total cost of ownership. So now compare this with the cooling towers for the Q supercomputer at Los Alamos. Recall that the blade servers that used nearly 16 watts in 2004 could perform better today, but draw probably a few watts, if that. And this design also offers design lessons about reliability. That is, the tortoise can beat the hare. If mean time between failures is shorter than computation time, Green Destiny at the upper right beats Q, just as a Camry eventually beats a blazingly fast but unreliable Formula One car. The actual mean time between failures is often set, you see, not by hardware, but by software bugs, by human error in integration, installation, configuration, operation, repair, upgrade, and so on. Also, 10°C cooler operation typically doubles equipment life. Well, at 1.6 volts, a 0.5 gigahertz Pentium 3M compared with the Transmeta TM5600, 600 megahertz that you saw earlier, that means 122°C versus 64°C, almost a factor 2 difference in chip temperature. That implies a 60 times longer hardware mean time between failures for the efficient cool blade server. So as Dr. Feng said, less power, less heat, passive cooling, and greater reliability meant his cluster computer needs better than faster and more demanding machines. Makes sense. Progress continues and adoption expands. So a team, including our Stanford colleague, Jonathan Kumi, published in Science magazine a wonderful summary of how that vision and more has been realized. This Tufty quality summary graphic shows how in just 8 years, the world's data centers installed 26 times more storage capacity. They carried 11 times more data traffic. They did 6.5 times more computing. They installed 30% more computers, and yet they almost completely offset that activity growth with a combination of nearly 5-fold more efficient servers, including idle management, over 8 times more efficient storage, and nearly 2 times more efficient infrastructure loads. So computing went up 550% in 8 years in the world. Electricity use for computing went up only 6.5%. All these areas still have a long way to go. For example, go back a minute to cooling. Conventional data centers have long used costly and inefficient refrigerative cooling units called CRACs, C-R-A-C. So we looked at alternatives. And if you look at the kilowatts per refrigerative ton, which is 3.52 thermal kilowatts, you know why it's called that? That's the rate of cooling delivered by melting a short ton of ice over a 24-hour period, because we used to buy big blocks of ice from a truck that were cut out of a frozen lake somewhere up north. And that's how we did air conditioning before we had refrigerative cooling. Okay, so you see it costs generally less than zero to reduce heat loads. There are ways to radiate heat to the night sky very cheaply. You can use an airside economizer, which is kind of the equivalent of opening a window, but using equipment. You can use a waterside economizer, that is an efficient cooling tower, desiccant or absorption using waste heat. And that can be extremely efficient. You can use a water-cooled central electric chiller system, quite expensive, or an air-cooled central system or a CRAC. So you see there's a lot of cost as you get into the less efficient ways. They cost more, they work worse. And also important, of course, is how do we get heat off the chips? Well, you know, the water has almost 3,500 times as much heat capacity as air per unit volume. You remember that from the two big sort of balloons and a little cup of water in a cooling lecture. And water needs an order of magnitude less energy to move it than air does for the same heat transfer. You can more precisely and consistently deliver and control and efficiently heat exchange water than air. And it can be straightforward and safe to mix electricity and water. A lot of industries have done so for a long time. So why not just conduct or heat pipe heat to the backplane and then liquid cool a heat sink there? That is indeed done fairly widely now. And to get rid of the heat, you could just run a heat pipe up to a radiator. There are other tricks you could do. Of course, the key is to make the equipment very efficient to start with. You know, our once heretical notion of wholly immersed liquid cooled supercomputers has now become widely accepted and commercialized. And now more designers understand, as Christian Bellotti pointed out, that just a passive radiator can keep a device played at 75 C, which is pretty comfortable for a modern chip. Well, asking the right questions about heat management opened up many important opportunities. One, of course, is to bury dead servers that are running apps you're not running anymore. Just turn them off, take them out, recycle what you can, rather than just leaving them running in the rack as if you would need them someday. Virtualization means that you, instead of running one app on each physical server, you put multiple apps on a server by making it a bunch of virtual servers, each one doing one thing, and then you get rid of the rest of the physical servers. Good for 4-fold savings or more. Rather simple idea, put the hottest and most heat tolerant and least mission critical servers at the top of mixed racks. Failure rates are 3 times higher up there. Why do you suppose that is? Oh, it's hotter up there. So put the most critical, least heat tolerant things at the bottom of the rack. Enable all power management features, saves upwards of 20%. Insist your vendors do that when they send you the stuff. And if you temporarily disable them, put them back. Use science-based specifications for dry bulb temperature and relative humidity based on what the equipment actually likes or needs to operate reliably. You typically don't have people in the space. If you did, they could wear one of those phase change vests, for example, and be very comfortable in a warmer room. You can broaden your humidity ranges. Make sure you calibrate your sensors so they're not fighting your room air conditioners if you haven't gotten rid of those. Use variable speed on chilled water cracks. Turn off any you're not using. Control your ventilation according to CO2 levels. Only the people care about that. The servers don't mind. And make sure your outside air economizers, which in Northern California are good for about 81% energy savings, are used and well maintained. Just proper airflow can save you about 3/4 of the cooling energy in a typical data center. And of course, fix the real estate model so you're not cramming more watts into less area. But the biggest insights came from drawing an analogy to our earlier pumping diagram and applying that to a data center. So let me share that with you. 2/3 of the fuel fed into the power plant is lost in the plant and the grid. Half the metered electricity is then lost in the cooling system and the uninterruptible power supplies, which are together half the total capital cost of the facility. And they're lost before they even get to the servers. Then half the server energy doesn't get to the chips because it's lost in inefficient, usually very underloaded power supplies, and in lots of fans to take that heat that largely shouldn't be there off the motherboard into the room so we can do dumb things with it. By the way, NTT facilities in Japan pioneered DC power supply. That eliminates the power supplies in this diagram. Now, the next problem is severe underutilization of computing resources, partly through lack of virtualization, all those zombie servers that sit there eating power and doing nothing. Well, the resulting energy flow, the tiny little yellow stalk at the lower right, is about to disappear. So let's magnify it before it does. Next problem is bloatware, running lots of unnecessary threads and processes and making simple tasks very complex because compute cycles were cheaper than programmers' attention. And anyway, somebody else was buying the energy. Downstream of all that, you may even have inefficient building or business processes. Well, in all, if you look at the red numbers at the bottom, only a few hundred thousandths, a few times 10 to the minus 5 of the original fuel energy is ending up delivering customer value. Where should we start fixing this? Right, downstream, start at the end. First, we write elegantly terse code, optimally compiled, with the goal that every compute cycle is a needed and wanted one. I had assumed when we were doing this work that it might save an order of magnitude in compute cycles to write good code. Recent tests suggest it's 2 orders of magnitude. And of course, the shift to mobile devices now makes this important because efficient code stretches battery life. Well, then we can at least quadruple server efficiency. Now, that's a decade ago. We could do better now. And then the servers need far less cooling and far less power supply, both of which can be done in far smarter ways than normal methods. And we could even cut the utility losses in half by using fuel cell trigeneration, and that reduces total capital cost. It's cheaper than the uninterruptible power supply it replaces. Well, if you multiply those savings from downstream to upstream, from right to left, you get at least 2, maybe 3 orders of magnitude, factors of 10 energy savings. In the project for whose charrette we prepared this diagram, our partner EDS, not yet quite bought by Hewlett Packard, said that if our recommendations had all been adopted, we'd have saved about 95% of the energy and half the total capital cost. In fact, the ultra-conservative client rejected most of our recommendations, even though EDS agreed with nearly all of them, so we could only triple the efficiency at the same capital cost. Pretty disappointing. Well, next time. So to summarize the concepts that these examples have illustrated, here are a few design maxims that I have found useful in practice. Many people have noticed that the path to simplicity leads through the thickets of complexity. So Einstein emphasized making things as simple as possible, but not simpler. And he put supreme value on tunneling through the complexity barrier. But as I mentioned in lecture 1, the author of The Little Prince said that simplicity comes from not from adding, but from subtracting. A thought you will also recall was echoed by the sculptor Michelangelo. Epistemologist Gregory Bateson urged us to seek the pattern that connects. Developers Mike and Judy Corbett, who designed the brilliantly integrated Village Homes project in Davis, California in the 70s, could spot that pattern by noticing unexpected multiple benefits. Although I've always felt it's better to avoid problems to design them out than to have to solve them. You could say a problem is a symptom of misstating the design goal, and it vanishes when you get the goal right. But all the big mistakes in design are made on the first day, when we decide what we're not going to consider, and when we often set the system boundaries too tightly, too narrowly, ignoring Eisenhower's maxim about making the problem bigger, and with it, the solution space and the opportunity. It's lately become fashionable to teach that design is the art of compromise and trade-off, as if it were a way to negotiate with yourself to make sure you can't do what you want. Well, the late Jay Baldwin, a wonderful student of Bucky Fuller, was once staring out the window in a California classroom where he was being taught this nutty idea. And he was watching a pelican catch a fish. And he realized that what the lecturer was saying couldn't possibly be right, because nature doesn't compromise. Nature optimizes. That pelican, he realized, is not a compromise between a seagull and a crow. It's the best possible pelican. After 90 million years, it's a really good pelican. So if you find yourself needing to compromise between desirable design goals, it usually means you haven't yet found the right statement of the design problem. Keep at it, you'll get there. And then you'll experience what David Oakey at Interface felt when his selenium carpet solution suddenly came together. And he said, God must be an environmentalist. When we figured out what questions to ask in order to make the thing a good natural capitalist product, everything suddenly fell into place. We got every attribute we wanted, none we didn't want, and a bunch of cool stuff we never thought to ask for. That's often what happens when you truly cultivate beginner's mind. We just need to keep it simple. Take stuff out until almost nothing is left. As the race driver Colin Chapman said, simplicate and add lightness. Simplicating is not what we're normally taught. Children do it just fine. If only we could remain as brilliantly free as children are from assumptions and preconceptions and what Herman Kahn called educated incapacity, and is inspired by natural models. We're the problem. We just need to clear away those obstacles between our ears. I hope these little case studies from actual industrial projects will help you ask the right design question, the one that makes the answer obvious. If you're mystified, just ask yourself what my reflective Sumatran swinger buddy would do, and try it. Thank you.